Hi friends, today we are going to see that how the DSP algorithms or the DSP processors manages to use a fixed point and floating point number representation. So before that, we need to understand what do you mean by a fixed point number and a floating point number. Now, let us take an example. We have a number called 9.375 to the base 10, that is in the decimal, and its binary representation we have seen is 1001.0110, right? So based on this binary point placement, we have two number representation. If the computer systems or the resistors inside a DSP processor work with a fixed position of this point, for example, I keep my first digit as an integer, point all the rest of the digits as a fraction, or first two digits as my integer part, point rest of them are the fractions, and so on and so forth. The point position is not allowed to move. Okay, so we have to fix this point position. If the point position is fixed inside a DSP or inside a processing, then that number is called as a fixed point number. Okay, and if the point is floating, then we can call it as a floating point number. It is not mandatory to keep it floating. Floating means not it will always change the position. It is not so. Okay, we will come to that point. So based on, okay, I can write like this, based on the position of binary point, we have two number representations. One we called as fixed point and second we called it as a floating point. You cannot float the point anywhere. There is still some restriction, but let us first not go that into detail. Okay, so this is fixed point and this is floating point. Now let us understand what is a fixed point. Okay, now in fixed point algorithm or in fixed point numbers representation, because in DSPs we normally use additions and multiplication, so I will be only concerned about the numbers which will undergo addition and multiplication, because that is the only two processes that we use while implementing a digital filter. If you have seen direct form 1, direct form 2, everywhere we will use a delay block, and the delay block will have a coefficient which will be delaying the sample value. That sample value will get multiplied by some constant, and then all the samples which are multiplied with constants are added together. Okay, so there will be addition and multiplication. So I will be using two arithmetic operations. One is addition and one is multiplication. So in a fixed point, let's say that fixed point number is being represented using b bits. Okay, and the fixed point is set after 8 integer values. Okay, the b bits are segregated like I have total b bits, okay, into which 8 bits on the right of the point and 8 bits on the left of the point. So we are having 8 bits on this side, 8 bits on this side, so there are total 16 bits. So in a resistor, when I have a 16-bit number, okay, what I'll do, I'll read the 8 bits, that will be my integer part, and I'll read the rest 8 bits, that will be my fractional part. Okay, so even if I write an integer 2, okay, with respect to 16-bit, I will write it as zeros. Let's say I'm writing 2. So because my point is fixed, I have to write it instead of 2 as 2.0, mandatory, because after 8 bits my processor knows that there is a point, okay, that now whatever starts is the fractional value, but all the values are 0, so does not matter. Understood? So 2 point, I cannot write an integer as 2. Even though it is 2 for me, for computer it is 2.0. Okay, for the algorithm it is 2.0 because I am using a fixed position of the point. Right? Now, it might happen that I have a number, okay, which is added with this 2. Let's say I add this number 2, let us make this 2 into binary form. So when I make it binary, let's take 4 digits, not 16, 8, 16 digits, because it will be too long string. So I will take 8 digits. So now the 2 will be represented as 0, okay, 1, 0, 0, point, 0, 0, 0, 0. Now what will be my addition will do? In my addition, I will arrange the next number exactly into this 8 bits, okay. And let's say I have a number of 8, so this is 0, 0, 0, 1, point, 0, 0, 0, 0. So what we have done? We have aligned the decimal number. So all registers will be programmed such a way that if the register is of 8 bit, first 4 bit will be integers and last 4 bits will be fraction. Okay. There will be no physical point present in the register. Okay, there will be no physical register or physical memory location or physical any component which tells that here is the position of the point. It is all about the algorithm will understand it as first 4 digits always integer, last 4 digits always fraction. Okay, so there will be, if I am using a fixed point and all registers are 8 bits, then there is no question of aligning the point, because the point will get aligned automatically, because after 4 bits my number is considered to be the fractional rest. Okay, so here it is 0, 0, 0, 0, point, okay, 0, then 1, 0, 1. Agreed? What has happened? Now my digit is of, now my digit goes 10. So this was 2, this is 8. Now I am getting answer as 10 when I add them. So this is how we do the addition. It might happen if suppose I consider some number which will produce let's say a carry at this point. What will happen? It will go as outside the addition. Okay, suppose I am adding 2 with 10, number will be 12. Okay. But still I have 4 digits. So let's take an example where here also there will be 1 and here also there will be 1. Okay. So if I want 1 over here, it will be 1 0 1 0, which is 10, and 1 0 0 1, which is 8. So I'm adding 10 with 8. Then what will happen? This 1 plus 1 will give me 0 here down and carry. Okay. That is a situation where we call that overflow has been occurred. So when I say overflow has occurred, overflow is a problem called overflow. Now, when the overflow has occurred, if a carry is generated at MSB. Now I am talking very much in the language of microprocessors. Okay, but with respect to maths, if I see that all my registers are of 8-bit length, isn't it? And everyone knows that after 4 bits, the integral part is over and fractional part has started. With respect to processor, I am adding 2 B bits number. And what is a B over here? B is 8. So this is B is equal to 8 bits and this is also B is equal to 8 bits. Okay. And while adding B is equal to 8 bits and B is equal to 8 bits, it might happen that my result will produce a 9th bit. Okay. And that 9th bit will be what? An overflow. Okay. So 2 B bit addition might produce an overflow. So the chances of getting an overflow is only in addition of a fixed point number. Okay. So this is a very major problem that we will go through because it will produce a good type of error in the DSP. So I hope you have understood that in fixed point, if I add two numbers, okay, then I can generate a 9th bit number. Or not always it will produce a b bit result. It might happen that it might produce a b plus 1 bit result, and that result, that plus 1 bit, is called as an overflow problem, or it is called as an overflow. Now we have seen that in the addition there could be a problem of the extra bit, and that extra bit is called as an overflow. When I deal with fixed point and we wanted to perform a multiplication, that time the major problem occurs is like I cannot have a total fractional number. I cannot have a number called 9.375 multiplied by 10.20, because based on the fixed point, as the binary point should remain the same, in multiplication the point will be shifted based on the two numbers. Okay, so that's why we cannot have a multiplication in the of the we say normal number which has a fractional part and integer part. So what we do is we do the multiplication of either integers together or fractions together. Okay, so in fixed point algorithm we will have a limitation of multiplying either because when you multiply two integers you will get an integer, when you multiply two fractions you will get fractions. Okay, so integers will give result as integers, fraction will give multiplication answer as fraction. So because of this limitation, what we always do is we always use fractional representation, or we normally put the number only in fractions in fixed point. So what I'll do, I will have an extreme 1 number on the 2 raised to 0th position point. All the other numbers will be represented as fractions. Okay, so I will be always looking into fractions when I'm using a fixed point representation. So we will see today that how to multiply two fractions in fixed point number. So I have a fractional number called 0.1001 to the base 2, and I need to multiply this number to 0.0011 to the base 2. So I have two fractional which are 4-bit long. Okay, I need to store this 4-bit long, and you can see that there is only 1 bit at the extreme edge. Okay, so when I do the multiplication of this number, the product, I am not wasting any more energy on doing this multiplication. You can try it on your own by using this multiplication. Okay, you see that 4 points after fraction, 4 points after fraction, so you will have a point after 8 number of digits. Okay, so the result you can check out with the calculation. As per my calculation, the result is 0.000 okay 11011. Of course it will be 8 bits, 4 bits after here, 4 bits after here, so number will be so the digit will get shifted by 8 bits. Okay, so if suppose the result also has to be saved, because I know that all the registers are programmed to have now how many bits? 4 bits. Okay, so if I am programmed to store that into 4 bits, then what is going to happen? Now I have an 8-bit number. How can I store an 8-bit number into 4-bit number? So here if I have a 4-bit number and I have a 4-bit number, then the result might be, or result is 8-bit. Correct. So if I say this to be b bits, this also b bits in general, then this will be 2b bits. That means twice that of the input bits. Okay. So there is a very big problem now. How can I store 8 bits into 4 bits? Isn't it? So it might happen in the floating point that the multiplication might result into higher data size. But I can perform multiplication on paper, that's not a problem. The problem will arrive when that we will see or check that what will be exact problem if I perform multiplication and then the result goes higher, and then I have to fit in somehow that into this. Okay, so what is the word length over here? It is 4 bit, but the word length over here become 8 bits. Okay, so this is what a fixed point multiplication is. So please remember the note that integral multiples will give integral answer, fractional multiples will always give fractional answer. Okay, we don't use them together. Okay, so because of this limitation, we always go with fractional representation. So whatsoever happens, I will always use a fractional representation. Okay, so I will always represent a number in fraction. And in many cases, the coefficients that you get for the filter is also a fraction, like 1 by 2, 3 by 4 and so on and so forth. Okay, so this is how we will be developing our algorithm henceforth. The next part of this is the floating point. Now, floating point is a much more scientific way of representing a number. A number in a floating point, let's say f, is denoted as m into 2 raised to c. Okay, where m is called as mantissa and c is called as characteristic. Okay, c sometimes is also called as e, which some books which called it as exponent. So now we have a mantissa and an exponent form. Okay, like for example, we can write 10 as 1 into 10 raised to 0. We can write 100 as 1 into 10 raised to 2. In the same way, now I will have a mantissa, okay, which again I will represent in fractions, and we will have a characteristics. For example, let me take an example. I have a number 4. Okay, my f is equal to, let's say, 4. How can I split this 4 into characteristic and mantissa? Now, before splitting this, let me also before splitting this, one more important thing which we need to remember is the m now is limited from half to 1. So the mantissa can either take the value as 0.5 or it can take the value as 1. So it can take the value as half or 0.5, or it can take maximum value as 1. Okay, so now how can I represent this number? Okay, I need to represent this number 4. Okay, so the minimum value that I can represent is 1 by 2. The maximum value that I can represent is 1. Let us take the lowest one, and if suppose my mantissa goes as 1 by 2. Okay, so what should be the value of 2 raised to c so that I can get the value as 4? We can easily see that here 2 raised to this c should be such that when I divide this number by 2, I should get 4. That is only possible if this number given, if the answer of this number is 8, isn't it? So, I want the actual result to be 8 by 2 because I have used this as 1 by 2. So, if I want the answer as 8 by 2, then I want that 2 raised to c should be giving me the answer as 8. When 2 raised to c will give me the answer as 8? When it is 2 raised to 3. So, I want that the mantissa, now the mantissa comes as 2. And the characteristics is 2 raised to 3. Now 3 I am representing in decimal, but it is not allowed. What I need to use? I need to use binary. So 3 in binary will be 1 by 2, 2 raised to 0, 1, 1. Okay, if I don't want in 3 numbers, then I can write 1 by 2, 2 raised to 1, 1. Or I can write 1 by 2, 2 raised to 0, 1, 1 if there are 3 bits associated with the exponent, okay, or with the characteristics. So a number 4 can be represented in this form where I have a mantissa which has to be in this length, and then it should be likewise 0, 1, 1. Suppose I use the mantissa to be 1. Okay, let's say that the mantissa is 1. So if I consider mantissa to be 1, I want the result to be 4. Mantissa went 1. Now 2 raised to c I want the answer. To get the 4 here, I want the 4 now. So if I have 1.4, then only I am going to get the answer as 4. How can I get 1.4? So I can write 1.2 raised to 2 will be 1.4, which is again 1.2 raised to, if I represent in 3 digits, it will be 1.2 raised to 0, 1, 0. So if I consider, now I have considered two extreme limits, you can consider anything in between and you have to adjust this characteristic such that it will give you the resultant as that same number. So here the mantissa is 1 and the characteristics is 0, 1, 0, which is 2 in decimal. Okay. So this is the integer. This is not fraction. This is integer. Now it might happen that not always I am going to have an integer very beautifully placed like this. So my characteristic will not always be positive. For a positive number, please listen carefully. For a positive number, for example 4 over here, the mantissa will always be positive. Okay. But the characteristics, okay, that is C, can take a positive or a negative value. That means when I write 2 raised to C, it is actually plus minus C, because that solely depends on what level of movement I am making of the point. Now the point is totally floating, isn't it? Now if I float the point, if I move the point, what I need to change? I need to change my characteristics. Now suppose I consider that my point, my resistor that I am working now has 1 point something, then I can adjust my characteristics to get the number 1 point something, isn't it? So that is the most biggest advantage of the floating point number. As well, we have seen that there is a problem of overflow or a problem of getting higher number of digits when we multiply or add the fixed point number. So in floating point number, I can adjust that mantissa to not overflow, to not come out or will not give me higher number of bits without changing its effective value. How can I do that? I can do it by just adjusting the characteristics, isn't it? So now I have two level of freedom. I can float I can keep the mantissa in the required bit length by changing the characteristics, the index of the two. So in this way, the floating point actually overcomes the problem of overflow in addition of the fixed point number. But multiplication, still there is some problem, because you cannot move characteristic like anything. If your characteristic number of bits are fixed, then you have certain level of limitation on what level of highest number you can represent. But always remember, the dynamic range or the range of numbers that you can represent using floating point actually increases exponentially with the increase in the characteristic. You increase 1 bit of the characteristic and the numbers that you can represent goes exponentially high. Okay, so as you start increasing the number of bits in the characteristic or in the mantissa, the level of numbers that you can represent increases exponentially. Okay, it is not restricted. There is huge range of numbers you can represent using floating point number. So I hope you have understood how to represent a floating point. But we will do the same thing, same twist with the floating point, that when I wanted to add two floating point number, how will I do it? And if I wanted to multiply two floating point number, how will I do it? So when you actually add two floating point numbers, let's say I wanted to add 4 into 10 raised to minus 2 plus 3 into 10 raised to minus 3. Can I add them? No, we cannot. We cannot add these two numbers. We need to adjust the index. Okay, either you increase the index here or you decrease the index here. If I make it this as 10 raised to minus 2, it will be 0.3 into 10 raised to minus 2. No, 30 into 10 raised to minus 2. Okay, so 30 into 10 raised to minus 2 and 4 into 10 raised to minus 2, you can add them. So what I need to do? I need to actually adjust the characteristic or the exponent. Once the characteristics are matched, or if once they are the same, then only I can add the numbers. Okay? In floating point number, the same concept applies. If the characteristics are not the same, you need to make the characteristics same first. Once you make the characteristics same, then you can add the mantissa. Okay? As you can see here, 10 raised to minus 3 is the small number. 3 into 10 raised to minus 3 is a smaller number compared to 4 into 10 raised to minus 2. So what I did? I changed the smaller number. In the same way, you have to change the characteristics of the smaller number. Let us, for example, take a problem. I have a number f1, which is 4, as we have seen in the previous case, and we have another number f2, which is 5 by 4. Okay, let us first denote f1 in terms of mantissa and characteristics, and we have seen that we can represent it as 0.1, let's say 5-digit representation, 1, 2, 3, 4. This is my mantissa. Okay, and the characteristics, that is 2 raised to, okay, the characteristics that I am showing is in 2 bits, that is 2 raised to 1, 1. Okay, so here my m1 is 0.1000 and c1, that is characteristics, is 1, 1. Okay, 11.0 you can write. Okay, then f2 I want 5 by 4, which is a fraction, so it will be 0. Okay, 101 0 0, which is in between 1 by 2 and 1, so I don't need to worry about it. So I made it as 0.1001. Okay, that is the mantissa, and the characteristic is 0.10. So here my mantissa m2 is 0.10100 and the characteristic c2 is 0, 1. Now, can I add them? Can I do f1 plus f2? No, we cannot, because the characteristics are not the same. Which is a smaller number? 5 by 4 of course is a smaller number. So what I'll do? I'll change the characteristics of the smaller number. I want the number to be 1, 1. If I will have 1, 1, that is 2 raised to 1, 1, it will be 2 raised to 1, 1 will be 8. Correct? So I'm getting numerator, I'm getting multiplication by 8. So how I need to adjust this number so that the resultant will be 5 by 4. Okay, so let us adjust f2. So for f2, okay, my c2, I'm changing it to 1, 1, which is 8. Okay, and I want what will be my m2. I don't know now. m2 has to change. Okay, now the resultant number is 5 by 4 I required, right? So I got 8 over here. I want denominator to be 4. That means here there should be something called as 32. Okay, and numerator I want 5. Okay, if you now manage it, it is 1s are, it is 4s are. Now I need to adjust this 5 by 32. Okay, now we have 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3, 2 raised to minus 4, 2 raised to minus 5. Okay, this is 1 by 2, this is 1 by 4, this is 1 by 8, this is 1 by 16, and lastly 1 by 32. Correct? So from here I will get 1 by 32. So one number will be over here, and second number I want it to be 5 in the numerator. Okay, I will get 5 in the numerator if I will have 32 as the base. Then I should have 4 in the numerator. So 4 if I want, then 8 4s are, that means I want 1 over here. Okay, if you are not very sure about it, let us check. I have put 1 under 1 by 8. So I am getting 1 by 8 plus 1 by 32. If I take the LCM of this, I am putting 32 over here. I am not putting 8 below. I am putting the highest number below, that is 32. Then 4 8s are 32 plus 1 over here. It will give me 5 by 32. So now my new mantissa, now my F2 with the new mantissa and new characteristic is 0, 0, 1, 0, 1, 2 raised to 1, 1. Now I will write both the mantissas which has been just modified. So I will write F2 modified. Now the F2 modified, if you will see correctly, it is 0, 0, 1, 0, 1, 2 raised to 1, 1, and F2, which is non-modified number, is 0.10100, 2 raised to 0, 1. Correct? Now see the bit positions. The bit positions has been shifted twice. If you see here correctly, I have shifted this once and I have shifted this twice. In the same way, I have shifted this once and shifted this twice. Okay. Why I have shifted that? Because in the numerator, I want to get a 1, 1. So I want here 2 ones. So I will shift this 0 out first and get 1 over here, and then shift one more time so that I will get 1 over here and 1 over here, right? So while shifting this towards the right, I will shift this bits also towards the right. Okay. Because I increased from 1 to 3. I went from 1, 2 raised to 1 to 2 raised to 3. So I have increased the order. That's why the number should not change. The number should not increase in order, magnitude. If you will directly put 2 raised to 3 and keep the bits as same, then the number will be wrong. It will not be 5 by 4. Okay. So you need to shift. How many times? 2 times. Because I want 1, 1 over there. So 2 shifts in the index gives me 2 shifts in the mantissa. Okay. Now you are free to add the numbers. So when you add the numbers, F1 plus F2, you have the index same for both, that is 1, 1. So I pull it out 1, 1, and now I will add the number 0. Okay, the first number is 0.10000, which is 4 times, plus 0.10100. Okay. So if you will add them together, okay, you will get M. Okay, you will get the result M to be 0.10101, and this mantis characteristics is 2 raised to 1. This is my final F. Now, if you check this number, that is this M, it should again be in the range of 1 by 2 to 1. If the result, now this will be in between 1 by 2 to 1, but if the result suppose does not comes or does not appears to be in the range, then further adjustment is required with this characteristics to get the mantissa in the range of 1 by 2 to 1. Okay, it is mandatory. So the result of floating point addition and multiplication might also result into overflow. Okay, whereas the major problem of overflowing the bits or getting increase in bits is of multiplication in fixed point. Okay, so if we just recollect the things, then in fixed point the major problem will be with respect to multiplication. Of course, there will be with respect to addition also, but the major problem that maximally occur is multiplication, because 4 point will give you 8 point. It's too much. Okay, and in floating point, the major problem will be with respect to addition also and with respect to multiplication also. So we need to take care of both of them and multiplication in fixed point when we are dealing with the fixed point and floating point number system. So I hope you have understood what do you mean by fixed point numbers and what do you mean by floating point numbers, and how we perform the arithmetics in a fixed point number and in a floating point number. Thank you.